Okay, welcome back everyone. So in this lecture, we're going to take what we've learned about case control studies and think about how we can use the data collected from them to calculate measures of association between our exposures and our outcomes. So for a case control study, even though we recruited people who were cases with our disease outcome and our controls, and then we look back in time, we can set up our 2x2 tables in the same way that we set up our 2x2 tables for cohort studies. And for cross-sectional studies, it can be the same. So, and I highly recommend you keep it the same so your calculations work. So for case control studies, remember we first select our cases and controls, and those numbers go in the columns. And then for the rows, we're putting in the numbers of the number exposed and the number not exposed. Okay, so if we go down the column of cases, we have cell A, which would be our cases who were exposed, and then we have cell C, which was our cases who were not exposed. And then for controls, we have cell B, which is our cases who were exposed, and cell D, which is our controls who were not exposed. So, as always with the 2x2 table, sorry guys, with the 2x2 tables, this is sort of I just want to point out this is the simplest of cases, right? Because, not is it always so clear that we have a dichotomous or a binary exposure where someone is absolutely exposed and absolutely not exposed. And this will come up in the lab assignment that, we can have degrees of exposed and not exposed. We can, if we look at, let's say, physical activity, we can have someone who's completely sedentary, someone who participates in less than 2 hours of activity a week or more than 2 hours of activity a week, right? However you want to cut it. And so the 2x2 table, it could be a 2x3 table or a 2x4 table, but the 2x2 table is just the easiest to work with. So again, okay, so for our case control studies, we have each of our cells that break out cases exposed and not exposed and controls exposed and not exposed. And then of course we can add up along the rows or the columns. Okay, so in case control studies, we intentionally selected people with and without disease. And this is what I was referring to at the end of the last video. Therefore, we can't know from case control studies the incidence of disease among our exposed and unexposed, right? We're not looking to see how disease develops among our exposed and our unexposed. We have intentionally selected the number of cases we're going to look at and the number of controls we're going to look at to understand their exposure history. So because we cannot calculate incidence, we also cannot calculate risk ratios, relative risks, incidence rate ratios, all of those incidence rates and relative risk measures that we learned last week. We cannot calculate it because we cannot get incidence from our case control studies. But what we can do in case control studies is go backwards from the disease. And what we're going to do, and I'll walk you through this, we're going to be introduced to a different idea, which is the calculation of odds, which is different than probability. So far we've been working with probability with our incidence measures. Now we're going to work with odds, and I'll introduce you guys to this. But what we can do is go backwards from disease and calculate the odds that our cases were exposed to our whatever we're interested in, and the odds that our controls were exposed. And then we can calculate those two and create a ratio of our exposure odds. That's just a highlight of what we're going to learn. Okay, so I like this example a lot to show you how we cannot get incidence from a case control study. I'll be honest that I didn't really think about this issue as a student. And then as an instructor, I was like, oh gosh, how do I explain this? But I think this is a really good explanation of why, if we ever try to calculate incidence or relative risk from our case control data, we're going to be totally wrong. Okay, so what if we ask the question, is there an association between bottle feeding versus breastfeeding and ear infections? So say we decided to recruit 100 infants with an ear infection, they would be our cases, and we found that 50 of those are bottle fed and 50 of those are breastfed. And then for our controls, we recruited 100 infants without an ear infection, and we found that 25 are bottle fed and 25 are breastfed. So here we can fill in our 2x2 table based on the information above. We have our 100 cases, 100 controls. Among our cases, they're 50-50 split. And then among our controls, 25% bottle fed, 75% breastfed. Okay, so say if we could calculate the incidence of ear infections among this group. Never actually do this, but say we could. So we would calculate the incidence of ear infection among our bottle-fed kids, which would be 50 over 75. We then calculate the incidence of ear infection among our breastfed babies, 50 over 125. And then we can calculate a relative risk, or in this case, if we were pretending, a cumulative incidence ratio. And we end up with a relative risk of 1.68. So from these data, if you calculated them completely incorrectly, you would find that bottle-fed infants had a 68% greater likelihood of ear infection compared to breastfed infants. And you might think that you have the right answer to the story. But what happens if we recruit 1,000 controls versus 100, right? But they're bottle-fed in the same proportions as our original thing. So this is just a decision that an investigator makes. Oftentimes in case control studies, it does not need to be a 1-to-1 ratio between your cases and controls. It actually increases your sort of efficiency of the study if you have, say, a 1-to-2, 1-to-3, or 1-to-4 ratio between your cases and controls. Once you get above a 1-to-4 ratio of controls, you're get really diminishing returns, and it's not worth it. But this is often a way that scientists increase the numbers of people in their studies, to increase the what we call the power of the studies to detect associations without actually having to find more people who have their disease. They can increase the ratio of cases to controls. So what if we did that in this case? Again, we decided, oh, you know what, I want 100 controls, but they're, breast versus bottle feeding at the same exact proportions as in our 100. So we can again fill out our 2x2 table and incorrectly calculate the incidence of ear infections among our bottle-fed, breastfed, and then calculate a relative risk. Here, our relative risk is 2.83, much, much higher than we saw above, even though the exposure was happening in the same proportion in our control group of 100 versus our control group of 1,000. So if we did the study this way, we would be able to say bottle-fed infants had 183% greater likelihood of ear infection compared to breastfed infants. Same proportions, just a decision by the investigator, and we end up with a 68% greater likelihood versus 183% greater likelihood, completely different. So the bottom line of the story is that disease frequencies, the incidence of disease, are real phenomenon. Like in the real world, children are actually getting diseases at specific incidence rates, and they should not be influenced by our study design or decisions. It is completely up to the investigator how many people they're recruiting. That's not reflective of the true incidence of disease in the underlying population. It's a decision by the investigator. And these decisions can change your outcome if you use the data incorrectly. So the bottom line from all this is that you cannot calculate incidence from case control studies. And because you cannot calculate incidence, you cannot calculate relative risks. So don't try. Okay, so what do we need to do? If we can't calculate relative risks and we can't calculate incidence, we need another way. We need a different measure of association between our exposure and our outcome. We need a different way to be able to calculate, is our exposure associated with our disease, and in what direction is it associated? Is it a risk factor or a protective factor? And so as I mentioned above, we can start to think about odds and odds ratios. So previously, when we calculated incidence, we were calculating a probability measure. And the way we calculated that, this is incidence. We had the chance of an outcome occurring divided by the total number of possible outcomes. We calculated incidence. Now we're going to do something different. We're going to start to calculate odds. Odds has a different denominator. Odds are the probability of an outcome occurring divided by the probability of an outcome not occurring. So instead of that denominator being your total, it's just the number that the event didn't occur in. I'll go through the 2x2 table. Okay, so let's first calculate the odds that a case was exposed. So the odds that a case was exposed are the probability that they were exposed, which is A, divided by the probability that they were not exposed, which is C. So again, if we were to calculate incidence, we'd be calculating A over A plus C. To calculate odds, it's just A over C. Then we can do the same thing to calculate the odds that a control was exposed. B, the probability of the outcome occurring, B, over the probability of the outcome not occurring, D. So the odds that our control was exposed is B over D. Then if we want to calculate a ratio of the two, so what is the odds of that a case was exposed divided by the odds that a control was exposed, the ratio of the odds. We put A over C divided by B over D. And if you guys remember how to divide by a fraction, you basically flip the second one over. Trust me on this. So I'll go up here. So the A over C divided by B over D, if we figured this out, it would actually end up being A over D divided by B over C. And this is often called the cross product because we're basically multiplying the cross products here. A times D, wait, did I say that correctly? A times D over B times C. So A times D is our numerator, this cross product, and B times C is the denominator, this cross product. So here's the bottom line. You're calculating an odds ratio, you set up your 2 by 2 table, AD over BC, that is your formula. That should be written into your brains, AD over BC to calculate an odds ratio. So again, our odds ratio is the ratio of the odds that cases were exposed to the odds that controls were exposed. It's essentially equivalent to a relative risk measure, but we're using odds, we're not using incidence. Something, some of you may notice, okay, so this is actually a ratio, an odds ratio of exposure. It's the odds that our cases were exposed compared to our odds that our controls were exposed. We don't really care about the odds of exposure among people with disease. What we actually care about is the odds of disease among people who are exposed, right? So like in our public health interventions, we want to know how many cases of disease or how much disease was the result of exposure. So just know that although we're calculating exposure odds ratios, it's mathematically equivalent to a disease odds ratio. So this is going to be able to tell you, it's a lot of talking to be able to tell you this odds ratio is going to be the mathematical equivalent of the odds of disease among those exposed compared to the odds of disease of those unexposed. Bottom line though, if you're asked to calculate an odds ratio from a case control study or from anything, you can actually calculate an odds ratio from a cohort study or a cross-sectional study too. We just don't introduce it in that way. But odds ratios are cross products, AD over BC. And in the same way we dealt with our relative risk, the null value or the no association value for odds ratios is 1. So if an odds ratio ends up being 1, that means there is no relationship between our exposure and our outcome because the odds of our cases being exposed was the same as our odds of the control being exposed. So you divided the number by itself and it turned into 1. If our odds ratios are greater than 1, then the odds of exposure is greater in cases than in controls, and therefore the exposure is a risk factor for your outcome. Again, same thing as relative risk. An odds ratio greater than 1 indicates the exposure is a risk factor. Meanwhile, an odds ratio less than 1 means the exposure was a protective factor. Same thing with relative risk. Okay, so I know I went through that fairly quickly. I posted two more videos about odds ratios. There's one with someone working through the problem, and then there's another one discussing odds ratios versus relative risk. I chose these videos because I think they present things very simply and nicely, and it gives you an opportunity to see the problem being worked through. So I would highly recommend at this point, or I have one more slide to finish up, immediately after, you go and you work through the problems in the video, and then you go and do the lab assignment. Bottom line though, set up your 2 by 2 table with your case control study data. An odds ratio is AD over BC, and we treat odds ratios the same way we treat relative risk as far as the null value, the value indicating protection, and the value indicating risk. Okay, so the problem though is So we've calculated your odds ratios, you're good to go, you understand your relationship between your exposure and your outcome, but people don't really understand odds, right? I don't know, some people have been exposed to odds in horse racing or betting on football, but understanding odds in terms of your likelihood of getting sick, like what are your odds of getting sick? We may use that in common language, but it's not, the math isn't really well understood. And what we truly care about is risk. What is someone's risk of getting a disease or a health outcome when they're exposed to something? And so the good thing about odds ratios is that they can approximate the relative risk if the disease is rare. And a rule of thumb that's used is if the incidence of the disease in the general population is less than 10%. And this assumption is called the rare disease assumption. So if you have a rare outcome, you're fairly safe calculating an odds ratio and assuming it is, or talking about it in terms of likelihood or risk. If you have and that works well, right? Because in case control studies, we tend to study rare diseases. So our odds ratios are reflective of our risk ratio. They're mathematically similar enough that we're comfortable with that. The problem comes about, though, if you're studying a really common outcome and your odds ratios can be very far from what your relative risk would be if you did the same calculation. So here's a little figure, right? So if your baseline risk in your population, your incidence in your population is, here's about the 10% mark. There's very little deviation from these lines, right? They're all about the same. And they don't overestimate the relative risk that much, a very tiny little amount. But say that the risk of your outcome in your population was, say 94% of your population had your outcome of interest. If you ended up with an odds ratio of 2, that is 100% overestimation of what your relative risk would be if you calculated it with the same numbers. It gets even worse if you have a stronger association between your exposure and your outcome. So say you ended up with an odds ratio of 10. So people exposed had 10 times greater odds of getting your disease outcome, of having your disease outcome. You would be overestimating if you had measured relative risk by 700%. So the bottom line with this is that our odds ratios work well at approximating risk when we have rare diseases, which is when we would normally have them, use them because we've done a case control study. You will often see odds ratios talked about when they're calculated actually from cohort study data. The reason for that is that it's sort of a lazy thing because our computer programs tend to spit out odds ratios instead of relative risk. And if you read a paper where you have a really common outcome and they're reporting an odds ratio, you should know that that's probably an overestimate of the relationship between your exposure and your outcome because you're using an odds ratio with a really common disease. And the investigator would have been in a much better position if they had taken a few extra steps and calculated an incidence ratio or a relative risk rather than an odds ratio. Okay, so that was a quick review or a quick introduction. I want to, again, highly encourage you, I'm going to go back to this, highly encourage you to look through the 2 other videos so you can start to see some numbers plugged in and understand how to actually calculate the odds ratios, and then do the lab assignment to get practice on the odds ratios. Okay, thanks guys.